Consider a situation where we need to keep a constantly changing collection of items, like words in a dictionary or numbers in a database. Binary search trees are a logical option for keeping things organized and facilitating effective search. However, if these trees are not managed carefully, they can become unbalanced, which can affect search times and performance. This is when red-black tree enters the picture. In addition to being a tree data structure, a red-black tree is an effective self-balancing binary search tree that makes sure its height stays logarithmic despite varied insertion and deletion operations. This balance, which is a cornerstone of many essential algorithms and data structures, is necessary for ensuring rapid access to data. In today's session, we are going to cover everything you need to know about red-black tree data structures and its algorithm. But before we begin with today's topic, I would like to request you guys to subscribe to our channel and click the bell icon to come across multitudes of updates from Intellipaat YouTube channel. First of all, let me take you guys through the agenda that we have for this session. We will start by understanding what is a red-black tree. In order to understand the topic better, I'll try to cover the prerequisites like binary search tree and AVL tree. Then we will move ahead and learn about the properties of a red-black tree. Then we will try to understand how insertion, deletion and search operations are carried in a red-black tree. After that, we will look into the coding implementation of the red-black tree. And lastly, we will try to look into the applications of red-black tree. And with this, we will finally conclude our today's video on red-black tree algorithm. I hope I have made myself clear with the agenda. So let's dive into the first topic on our list. What is a red-black tree? A red-black tree is a kind of tree data structure, and a tree is a non-linear data structure. A data structure is basically a way of arranging data in an organized and efficient manner in such a way that we can store and fetch data as quickly and efficiently as possible. Every tree data structure has a primary node called the root node. This root node has its subnodes connected to it with the help of edges. These subnodes of the root are called child nodes, and the root node is called the parent node. Each subnode having its own child nodes form a subtree. These subnodes serve as parent node for their own subtree. The children nodes share sibling relationship with each other, and all the nodes who do not have their own children are called the leaf nodes. These two child nodes of the subtree are also the leaf nodes. A binary search tree is considered a red-black tree if it follows certain properties which only a red-black tree possesses. In other words, a red-black tree is basically a binary search tree adhering to some specific strict rules or properties. To understand the red-black tree better, let us first understand what is a binary search tree. A binary search tree is a node-based tree data structure in which all the nodes to the left of the parent node contains data lesser than the parent's data, and the nodes in the right subtree of the parent contains data that is greater than that of the parent. Both the left and right subtree should form a binary search tree on their own. For example, here we have a binary search tree in which 10 is the root node. So all the nodes which are having values lesser than 10 should be on the left subtree, and the nodes having greater than 10 should be on the right subtree. So 5, 2 and 9 have values lesser than 10, and 15, 13, 17 are greater than 10. So these belong to the left side and these to the right side. Same applies to their subtree as well. Like 2 is smaller than 5, so it's on the left side of 5, and 9 being greater is on the right side. And same, 13 is on the left of 15 and 17 on the right of 15. In the best case scenario, the time complexity of a binary search tree is big O of 1. In average scenario, it remains big O of log base 2n or big O of h, where h is the height of the tree. And in the worst case scenario, its time complexity becomes big O of n, where n is the total number of nodes in a binary search tree. Another tree data structure closely related to the red-black tree is the AVL tree data structure. AVL tree is named after its creators G.M. Edelson-Velsky and E.M. Landis. It is a height-balanced binary search tree in which the balance factor remains between -1 and 1. If the balance factor of each node is between -1 and 1, then the tree is said to be balanced. Otherwise, the tree is imbalanced and it should be balanced. The AVL tree example over here shows a balanced AVL tree. In this, you will see that the difference of the left subtrees and the right subtrees levels is equal to 1 or 0. It is because I have taken modulus of the differences. In other websites or references, you will find this balance factors formula as if the difference of right subtree with the left subtree or the vice versa, which will create the difference in the signs of the resulting number. So in that scenario, it will be between -1 or 1. But I have taken the modulus of those difference, so we are neglecting the sign over here. So basically, our this balanced subtree has either 0 or 1 as its value. For example, for this 10, our left subtree has 2 levels and the right subtree has 3 levels. So the difference and modulus of the difference will give us 1. Similarly, 5 has 0 and the leaf nodes have 0 as their balance factor, making this whole AVL tree a balanced one. An AVL tree performs 4 different types of rotations in order to maintain balance between its nodes. The first one is LL rotation. In this case, we will have a left skewed AVL tree. But the problem with this is the balance factor of 10 is 2 because it is having 2 levels on the left side but 0 on the right. Similarly, the 6 is having 1 and 2 is 0. So 6 and 2 is balanced, but this 10 is having balance factor as 2, so it is not balanced. In order to create a balanced AVL tree, we will make an LL rotation in which this 10 will become the child of this 6 and this 6 will become the parent, giving us the balance factor of 0 in all the nodes. Similarly, RR rotation is kind of mirror image of LL rotation. In this, again this one is having 2 as its balance factor because there is no left subtree, but there are 2 levels on the right subtree. So in order to make it balanced, this one will become the child of 6 and 6 will become the parent, resulting in 0 balances of all the nodes. Third is LR rotation. In this one, the parent is on the left and the child is on the right side of its parent. So in order to make this tree balanced, we will first do a left rotation in which the 5 and 2 will be swapping their places, and then we'll perform a right rotation in which this 5 will become the parent, this 10 will come down to be the child of 5 and this 2 will remain its child. In this way, this imbalanced 2, 1, 0 will be balanced as zeros. The RL rotation is again the mirror image of LR rotation. To make this balanced, we will first swap the places of 5 with 10 and then we'll do a complete left rotation, resulting in this kind of balanced tree where this 5 will be the parent and 2 and 10 will be its child, resulting in 0 balance of the AVL tree. Knowing a little more about the AVL tree, its searching time complexity is better compared to other tree data structures, but due to its rather strict balance, AVL tree provides complicated insertion and removal operations as more rotations are performed. AVL tree takes more processing to balance its nodes. The reason for this is it takes a lot of rotations to stay balanced, while the red-black tree takes at most 2 rotations to balance its nodes. In some scenarios, only recoloring is required to make it balanced. This comparative relationship between AVL tree and red-black tree makes it necessary to have knowledge of both the concepts to better understand the importance and implementation of both of these data structures in different scenarios. Now a question may arise, can every AVL tree be a red-black tree? The answer is yes. Every AVL tree can be a red-black tree if each node is colored red or black. However, not every red-black tree is an AVL tree, since an AVL tree is strictly height balanced, but a red-black tree is not totally height balanced. Now we know what is a binary search tree and what is an AVL tree. So let us move ahead and dive deeper into the concept of red-black tree algorithm, starting with learning about its properties. It is a self-balancing binary search tree, which means it balances the tree by rotating or recoloring the nodes. It is called a red-black tree because each node in this tree data structure is either red or black in color. Every node holds one extra piece of information known as a bit, which represents the node's color. For example, 0 bit signifies the node's black color, whereas 1 bit denotes the node's red hue. The node also stores information comparable to a binary tree, such as a data component, a left pointer, and a right pointer. In the red-black tree, the root node is always black in color. In a binary tree, the nodes with no children are considered as leaf nodes, while in the red-black tree, nodes with no children are considered internal nodes, and these nodes are connected to the NIL nodes, which are always black in color. In the red-black tree, the NIL nodes are the leaf nodes. If the node is red, then its children must be black. To put it another way, there should be no red-red parent-child relationships. Every path from a node to a nil node in its descendants should contain the same amount of black nodes. And this makes up the important properties of a red-black tree. Now we know how a red-black tree should look and what the rules it must follow. Let us now understand the insertion operation in a red-black tree. While inserting a node into a red-black tree, one needs to follow certain rules in order to maintain the proper balance in the tree and handle red-red conflict, which simply means avoiding red parent-child relationships. Assume the newly inserted node is X. If this is the very first node in the tree, then it will be the root node and its color will be black, or else it will be red in color. If the parent of this node is black, then nothing needs to be done. But if the parent is red, check the color of the parent sibling, which is also called the uncle of X. If uncle is red, change the color of parent and uncle to black. Then change the color of parent's parent, that is the grandparent of X, to red, only if it is not the root node. Now assuming this grandparent as X, repeat the same steps again. Now if the uncle is black node or a null leaf node, which is also black, then rotations and recolorings are performed. Rotations are done exactly in the same way as it is done in an AVL tree, performing the same rules and steps followed in LL, RR, LR or RL rotation. For recoloring of nodes, if LL or RR rotations are done, then the color of parent and grandparent will be interchanged. But if LR or RL rotations are done, then interchange the color of the parent and X. Now let us look into an example to understand the insertion operation better. Here we have 5, 15, 2, 10, 12 and 20. Let's try to follow the rules and get a balanced red-black tree out of this data. So our rule says that the root node is colored black. So let's start with creating a root node which will be colored black, and this will hold 5 in it because that is our first data. After that we have 15. So our next rule says all the other nodes are colored red. So we will create another node and this will be 15 but with color red, and since it is greater than 5, therefore it will be on the right side of 5, meaning on the right subtree of 5. So let me have a connecting edge from here to here. After that we have 2. So 2 is smaller than 5 and is not a root node, so it will be a red node on the left side of 5. That's 2, and I'll again need this connecting edge. Let me color it black. Yeah. After that we've got 10. So 10 is greater than 5 but smaller than 15. So it will be on the left side of 15. Over here. Let's call it 10. And then a connecting edge. Right. But it looks like we have a red-red parent-child relationship, which is a conflict. So if the parent node is red, check the color of parent sibling. So in our case, our parent is 15 and its sibling is 2, which is having red color. So our rule says if uncle is red, change the color of parent and uncle to black. So we will be changing the color of parent and uncle to black. And then the rule says and change the color of grandparent to red only if it is not the root node. So is the grandparent of 10 a root node? Yes, it is. So in this case we will not be changing the color of the root node. Then comes 12. So 12 is smaller than 15 but greater than 10. So it will be on the right side of 10. Over here we have 12 and an edge. Again we have got a red-red conflict. So our rule says if the parent node is red, check the color of sibling. So our parent node is red but it do not have a sibling. So in this case, if uncle is black or leaf node, perform rotations and recoloring. So rotations we have LL, RR, LR or RL rotation. So in our scenario it is LR kind of rotation. So if LR or RL rotation is done, swap the color of grandparent and X. So let us have a log of who is the grandparent. So we have 15 as grandparent. Let me have a text box. So our grandparent is 15, which is black in color, and our X is 12, that is red. So we will be needing this data when we are recoloring. On doing LR rotation, we will be first switching these nodes. So 12 will be here and 10 will come over here. And after that, this whole assembly will be moved on clockwise direction. So 12 will become the parent and 15 and 10 will become child of 12. Like this. And then we will be doing the recoloring. So this 12 will be colored as black and 15 will be colored red. So now our red-black tree looks balanced. Lastly, we have 20. So 20 is again a new node, so it will be a red node. And it's greater than 15, so it will be on the right side of 15. Let's make it 20. And we will be needing an connecting edge. Okay. But again, we have red-red conflict and the uncle is red in color. So let's look into the rules. If uncle is red, change the color of parent and uncle to black. So this parent's color and the uncle's color, oh sorry, this is the parent and this is the uncle. So their colors will be changed to black, and then grandparent to red, only if it is not the root node. So the grandparent of 20, that is 12, is not the root node, so its color will be red. Yeah, we don't need this anymore. So this is our final red-black tree. Let's look into the properties. So the properties says that the root node should be black in color. The node which is after the root node should be red, and it should not have a red-red parent-child relationship. And lastly, every path from root node to its descendant nil node should contain the same amount of black nodes. So are we following all the properties? Our root node is black. We do not have a red-red parent-child relationship anywhere. And the number of black nodes from root to leaf is 2 in all the cases. 1, 2, 1, 2, 1 and 2. So yeah, we have got our balanced red-black tree. Now let us quickly look into the Python program to implement insertion operation in the red-black tree and try to understand the code in detail. Okay, so we are in our Python program, and the node class is defined over here, which represents a node in our red-black tree. It has a constructor which initializes the node's data members. Each node has a reference to its data, its color, that is either red or black, its parent node, and its left and right child node. After that, we have the red-black tree class, which contains a constructor to initialize the root and leaves of the tree. The tree's root is initially set up as a special node named R node with the color black. This node simplifies the boundary cases during the insertion and balancing processes and serves as a representation of tree's leaves as well. Then we have the left rotate function, whose job is to promote the right child to be the new parent while following the binary search tree properties. This is done by saving one of the nodes into a variable and then performing some swapping operations in order to get the final balanced red-black tree. So this starts with saving the right child of node X into a new node Y. Then this right child of node X will be updated with the left child of node Y. By doing this, the right child of node X has already lost its original value to the left child of node Y. So where does this original value of right child of X go? It is saved in this new node Y. After that, we assign the X as parent of Y's left child, only if it is not a null or a leaf node. After that, we make the Y's parent same as the parent of node X. Then we check if X is root node or not. If it is the root node, then we make Y as the root node as well. But if it is the parent's left child, if X is its own parent's left child, then we replace it with Y. And if X is the right child of its parent, we still replace it with node Y. After replacing x's with y, we make this x as the y's left child, and then we make this y as parent of node x. In this way, we keep swapping places of x with y, and then finally we get our desired left rotated tree. The right rotate function works in the similar fashion. The only difference is it works opposite to the steps which we have performed on the left rotate operation. After the left and right rotate, we have got the insert method. This insert method is used to insert a new node into the red-black tree. It creates a new node with the given data, assigns red color to it, and assigns it as a child of the R node. Then it calls the insert recursive method to put the node in the right position according to the binary tree structure. And then it finally calls the fix insert method to check for the red-black tree property violations and correct them. After that, we have got the insert recursive method, which recursively traverses the tree searching for a right position for the new node. If the current node is the prime node, that is the R node, this new node will be made the root node of the tree. In every recursion, the method checks if the new node is greater or smaller than the current node, and according to that, it traverses to either left or right subtree until it finds the right spot for the new node to be inserted. So this code works on the left subtree. It checks for the data. If it is lesser than the data of the current node, then it goes to the left subtree and searches for the right place. And this part of the code works on the right side of the subtree. After this, we have the fix insert function, which is responsible for maintaining the properties of red-black tree. First of all, it checks if the parent of the current node is red. So if it is having a red-red conflict, then we'll enter into this while loop. Here, we first check if the parent of the node is the left child of its parent, meaning if it is the left child of its grandparent. If yes, then we will create y as its uncle. Means if it is the left child of its parent, then the right child will be the uncle of this node. Then we check if the uncle is red in color. If yes, then we recolor the node's parent as black, we recolor the uncle as black, and then we recolor the node's grandparent as red. And then we make the current node's grandparent as the new current node. But if the uncle is black in color, then we perform left rotation in the current node's subtree. Then we recolor the parent as black and the grandparent as red. And then finally, we perform the right rotation in the current node's grandparent subtree. This whole process is in accordance with the properties of our red-black tree. Here we checked if our node's parent is the left child of its grandparent or not. If it isn't, then our node's parent will be the right child of its grandparent. So similar steps will be performed, but on the right subtree. At the very end, we ensure that our root's color remain black. Then we have the method to print the tree. It calls the print tree recursive function, and this print tree recursive function works until it has reached to a leaf node. This part gives a structural look to our tree, providing it with proper edges. And this part checks for the color of our node and then assigns R or B after the data present in the node. Upon completing a branch, it then moves on to the left branch or the right branch, means it moves on to the left subtree or the right subtree. From here we are passing the values which we on while creating our red-black tree. So let us try to run this program and check if the output matches with what we got. So this is the output. Here we have 5 as the root node, which is black in color. Then we have 2, which is also black as the left subtree. Then we have 12, which is red in color on the right subtree. Then we have 10 as black on the left, 15 as black on right of 12, and then 20 as red on right of 15. Let us try to match it from our tree. So this over here is our tree, red-black tree, which we created moments ago. So we have 5 black as the root, 2 on the left, 12 on the right, 10, 15 and 20 as red. So it exactly matches, which means our program works as expected. So now we know how insertion operation is carried out in a red-black tree. Let us now understand how searching algorithm works here. Since every red-black tree is a special instance of a binary search tree, therefore the searching technique of a red-black tree is similar to that of a binary search tree. Searching for a node starts with comparing the data value with the root node's data. If the value is equal to that of the root node, we have already found our match. But if it is smaller than the root node's value, then we take our search to the left subtree. And if the value is greater than the root node, then we start searching for a value in the right subtree. To understand this process better, let's take an example in which we'll try to search for the value 14 in the red-black tree, which we are looking at right now. So first of all, this 14 will be compared to the root node, which is 5. Since 14 is greater than 5, we'll move on to the right subtree. Then this 14 will be compared with 12. Since 14 is greater than 12, we'll again move on to the right subtree. Now we have found 15. Since 15 is greater than 14, therefore our search will be moved to the left subtree. Here we have got 14. Since 14 is equal to 14, we have found our right match. Similar to the insertion operation, the search operation in a red-black tree also takes O log n time in the worst case, because the height of a red-black tree is always O log n, where n is the number of nodes in the tree. Now we know how insertion operation is done and also how searching operation is carried out in a red-black tree. Now let us look into the delete operation in a red-black tree algorithm. In a red-black tree, deletion is a little trickier than insertion. A node can have 0 children, 1 child or 2 children when it is being deleted. If the node to be deleted has no children, simply remove it and update the parent node. If the node to be deleted has only 1 child, replace the node with its child, then remove the leaf node. If the node to be deleted has 2 children, replace it with the leftmost node in the right subtree, which is the node that comes after it in the hierarchy. The in-order successor node should then be deleted as if it had only 1 child. After a node has been deleted, violations in the properties of the red-black tree may arise. It might be the inconsistency in the number of black nodes from root to leaf in any of the branches, or it might end up having a red-red parent-child relationship. While performing the deletion in a red-black tree, we come across another interesting problem called a double black situation. This situation arises when a black node with no children is deleted. In this case, the leaf nodes of this removed black node form a double black node, producing an inconsistent number of black nodes in the tree. If a red node is deleted, no modifications are required because deleting a red node does not break the red-black tree characteristics. If a black node is deleted and the node replacing this deleted black node is a red node, then we need to recolor it to black to maintain the amount of black nodes. But if the deleted node is a black leaf node, then we will be caught in a double black situation. In order to handle this scenario and maintain the black depth property of our red-black tree, we need to perform rotations and recolorings. This process of rebalancing may involve actions in which we propagate this double black node's property in upward direction to its parent and then to the grandparent of the particular double black node until the properties of the red-black tree is restored. We have finally covered the insertion, searching and deletion operation in a red-black tree. Now let's have a look at the applications of the red-black tree algorithm. Red-black trees have applications in many branches of computer science and are especially beneficial when maintaining a dynamically ordered dataset. Here are some common uses of red-black trees. The text editors use red-black trees to efficiently implement functions like undo and redo. Cryptography algorithms like hash trees and Merkle trees use red-black trees. Red-black trees can be effectively used to index data in databases, enabling quick searches and data retrieval. Artificial intelligence algorithms like decision trees and game trees employ red-black trees. Algorithms for digital signal processing such as wavelet trees use red-black trees. It is possible to easily implement graph algorithms like Dijkstra's shortest path algorithm using red-black trees. Red-black trees can be used to implement dictionaries or associative arrays in which keys and values are associated. They enable fast insertion, deletion, and lookup of key value pairs. Red-black trees can be used to efficiently search and query geographical data in geospatial databases and geographic information systems, that is GIS, such as identifying points or regions inside a given range. These are only a few of the numerous uses for red-black trees. They are adaptable data structures that can perform efficient and balanced operations in a variety of settings. That's all we have for this session. I hope you have got a good understanding of red-black tree algorithm and how it is implemented. Thank you for being here till the end of this session. If you have liked this video, make sure to hit that like button and also consider subscribing to our YouTube channel to come across more technical updates like this.
Just a quick info guys, Intellipaat offers full stack web developer course in collaboration with E&ICT Academy IIT Guwahati. Through this course, you can learn everything from front-end web development to back-end web development from esteemed IIT Guwahati faculties and industry experts. With this course, we have already helped thousands of professionals in successful career transition. You can check out their testimonials on our Achievers channel, whose link is given in the description below. Without a doubt, this course can set your career to new heights. So visit the course page link given below in the description and take a first step towards career growth in the field of web development.